Hello and welcome to T3 Day 22 of Honors Precalculus. Today we're going to talk about standard deviation. Below are three different histograms. Find the mean and median for each of the distribution, then describe the shape of them. So the histograms tell you on this one on the left, the grade on a 10-point scale, and there are 2 people that got a 1, and then there's 3 people that got a 2. So if you add up all of those scores, remember it's going to be 1 plus 1 plus 2 plus 2 plus 2 because there's 3 of them here. You just have to make sure you add up all the right ones here and then divide by the total number of entries. What you'll find is that the mean is going to be 5.025. Just make sure you add up all the right ones, and then if you find the median by listing it all out, you'll find the median is 5, and the most common one, the mode, you can actually see that really easily, is going to be 5 as well. So what about the shape? How do you describe this? You're going to call it symmetrical because it looks like it's pretty symmetrical, maybe not perfect. Well, it actually almost is perfect, except over here, around here. It's symmetric across that middle value right in the middle. So it's a general description. You can do the same thing over here, and you find out that the mean on this one is 3.425. You find out that the median is 3, and in this case, the mode is 3 again. It's not always the same, but it can be. And for the shape, we're going to call this skewed right. Skewed to the right because it is in the direction of the tail. You can kind of think of it as it's going this way, so we're calling that skewed to the right. And on this one right here, it's very similar to the one we just had. If you do all the math out, you get a mean of 6.775 and a median and a mode of 7. And the shape in this case is going to be skewed to the left because the tail goes to the left here. It goes to the left. So now let's go back to practicing drawing our box and whisker plots. So we have the regular season home runs of Roger Maris, really cool player who played for the Yankees in the 50s and 60s. Side note, one of my father's favorite players along with Mickey Mantle. So when you do this out, the first thing you need to do is you put all of these numbers in order. So we just put them all in order, and then you find the center, and that center is actually going to be right here. And then you break it into the 4 groups. It's nicely divisible right there. And then if you add them all up and divide by the number of entries, you end up with a median of 19.5. Your quartile 1 is going to be 9 plus 13 over 2, because it's these 2 right here. So when you do that out, 9 plus 13 divided by 2, is 11. And then your quartile 3, sorry about changing colors, I'll try to keep it consistent here. Quartile 3, it's going to be right there. So that's going to be 28 plus 33 over 2. So that's going to be 30.5. So then that's going to tell us the IQR is going to be 30.5 minus 11, which is 19.5. So 50% of our data is in that middle range there. And then what you do is remember this 1.5 times the IQR is 1.5 times 19.5. We're widening it, 19.5, not 3, excuse me, 5. And you end up with 29.25. So what you can then do is you go above, so it's you quartile 1 minus and then quartile 3 plus that amount. So the upper amount here is going to be, remember, 30.5, and we're adding 29.25. So you end up with, right here, the upper level is 59.25. And you can go below here. So we could go below here and do the lower one, 11 minus 29.25. Well, that's just going to be negative. So you're never going to have a negative home runs in a season. So the question is, are there any outliers on this? Are there any outliers? Well, let's look at the list here. There is one outlier then, 61. That was a big deal when he did that. So this therefore would be an outlier because it's higher than 59.25, which is quartile 3 plus the IQR. So when we draw this histogram right here, we have our first value down here, which was 5, and then the highest one was 61, but that was an outlier up here. So the next one was, I think, 39 right there, so it's right about here. And then the quartiles were 11, so we do the longer one here. And then the third quartile is 30.5, which is right here. So we make this box right here. My boxes are getting a little better, like this. And then our median was 19.5, which is right about here. So we have 19.5 as our median. You can label this as 30.5 as quartile 3. Quartile 1 was 11. Then you have 5 and 39 here, and then this is the outlier right up here. This is a modified because we took out the outlier. And there could be more than one. So question 3, the table below gives the number of members of a typical family in 1955 and 2016. I'm assuming this is the United States, but let's find out. Not sure. So find the median family size in 1955 and 2016. So for the median, you're looking for that middle number there, and these are written in order, which is kind of nice. So we have these. So for 1955, it's going to be 7, and for 2016, it's going to be 4. What about the interquartile ranges? The interquartile ranges. So what you're going to do for that is you're then going to go and subtract quartile 3 and quartile 1. So for 1955, excuse me, not 1953, so 1955, you're going to do 8 minus 6, and that's going to be 2. And in 2016, the interquartile range, you're going to get by 6 minus 4, which is 2. So that's these two and those two right there. And then find the range of the family sizes in 1955 and in 2016. So in 1955, it's going to be 15 minus 3. The range is 12. But in 2016, you're going to end up with 9 minus 3 is 6. That's the range in family sizes. And then it says, which distribution is more variable? You're going to say that 1955 is more variable because the range of the numbers is larger. Range is larger. So that's how we're going to answer the question, which is more variable. And then if you find the mean, which is just the average of all the values, you add up all the entries and divide by the number of entries, and you get 7.57. And then in 2016, you get 5. So we use the IQR to measure variability when we use the median as a measure of central tendency. So that's that middle value. So IQR and median, what do we do when we use the mean as our measure of central tendency? Well, we're going to use something called standard deviation, which is going to be found by filling in a chart like this. So the first thing you do is you have all the entries here. So this is 1955, just 1955. And we know that the mean was 7.57. So the first thing we do is the value minus the mean, and you fill in that column right there. So when you fill that in, it looks like you get these values right down the middle here, these values. And then you take those values and you square them. So after you square them, you get all these numbers, and then you add them all together, and you end up with 81.69. So what we do with that number, what do we do with that number? You're going to generate this sigma x, and there are two different types of standard deviations, one for population, where we use the data from every, and one for a sample. So sometimes you can't get data from the entire population. So how do we do this? It's good to know where it comes from. So we got that 81.69. What you do is you divide by the number of entries, which is 7, and you end up with 11.67. And then you take the square root of this, and you end up with 3.42. This sigma x is the standard deviation, which is right there. So 3.42 is the standard deviation. So what we did is we averaged the sum of the squares of the difference right there. We got that. And then you take the square root, and you end up with this final number. That's the standard deviation. What this standard deviation tells us is, in the middle we had the 7.57. If you go to the left and right one standard deviation, so this would be right here, 7.57 minus 3.42, and this right here is 7.57 plus 3.42. What it means is that in this range right here, around 67% of the data will be in that range, will be there. 67% of the data will be in that range right there. It's pretty cool. Now, one thing that changes though is sometimes you have a sample of the data. So let's say instead of using all of the data, we just use 3 of the data points or 4 of the data points. You can still estimate. The sample. You can still estimate sigma s, but it's going to be, this time instead of sigma, it's going to be s sub x. The only difference in this case, if this was just a sample, so let's say these populations were just a sample of the entire population, the only thing that changes is you subtract 1 right here from the n. There were 7 data points. So if this was a sample for the entire population, what you do is to treat it like a sample, you subtract 1. What you end up with there is you get 13.6 13.615, and then S sub x, so if this was a sample, is the square root of 13.615, and you end up with 3.69. Again, this would be if this table was a sample of the population, which it is, then it's more accurate to subtract 1 here. It's more accurate. It adds in a little bit of variability in our numbers. What this also tells us, by the way, for standard deviation is that within 1 standard deviation, you have 67%, and within 2 standard deviations, you have 95% of the data is within 2 standard deviations. But it's all based around the central number here, that average. So medians and quartiles do a good job of summarizing the center of a distribution even when the shape is skewed or there is an outlier. When their data is somewhat symmetric, the mean and standard deviation is used. So this is good to use right here. Good to know. So here's Mr. Smith gave 2 tests and the grades are listed below. Find the mean and standard deviation of each using your calculator, then interpret each of the standard deviations in terms of the problem. So you can look this up and practice this in class, but you will be able to do all of this on your calculator, and it gets very repetitive if you don't practice it. In this case, when you add it all together, you end up with a mean of 86.57, and you end up with a standard deviation of 5.46. So what this means is if we center this at 86.57 and you go 1 standard deviation, so I'm going to try to do this sigma properly here, sigma x, and we go 1 standard deviation back like that, kind of draw it like that, start in the middle and go up. If you go each side, you add 5.46, so you end up with 92.03, and you end up right here with, let me get this right here, it's going to be 81.1. It means that 67% of the grades are going to be between there, or about that. So most grades are going to be between there. You can do the same thing down here. Oh, and the other thing you can say is that the average distance from each student's grade from 86.57 is 5.46. So the average student score is within 5.46 of the mean right there. So if you do the same thing down here, you end up with a mean of 86, and you end up with a standard deviation of 9.62. So what this means is that the average distance from each student's grade from 86% is 9.62. Again, the average distance from each student's grade from 86 is 9.62. So it tells you that the average distance from each student's grade from 86, that's the mean, is 9.62. And then about 67% of the grades lie between 86 minus 9.62, that's not 76.3, or 86 plus 9.62, which is 95.6.